Hello viewers, in today's session we are going to discuss another very important and conceptual problem from differentiation, right? So here in this session we are going to find out the derivative of sine log x with the help of first principle, right? So here we have the function f of x is equal to sine of log x, and here log of x is the natural log, right? So we can also use this notation, that is sine ln x, but here we'll prefer this notation, that is log log of x, right? So the definition of derivative is given by this limit, that is f prime of x, that is d by dx of f of x is given by the limit, that is limit h tends to 0 f of x plus h minus f of x divided by h, right? So this definition of derivative in terms of limit is known as finding out the derivative using the first principle. So here the function is sine log of x. So what we will do, we'll write limit h tends to 0, and then we have f of x plus h. So f of x plus h can be obtained by replacing this x by x plus h. So we have sine of log of x plus h, and then we have f of x, that is sine of log of x, and in the denominator we have h. Now see, to simplify the numerator, that is the difference of two sine terms, will make use of an important identity from trigonometry, that is sine a minus sine b. So here our a is log of x plus h, and b is log x. So sine a minus sine b is equal to 2 times cosine a plus b over 2, and here we have sine of a minus b over 2, where a is a log of x plus h and b is log of x. So let us find a plus b over 2. So a plus b over 2 is given by a log of x plus h plus log of x divided by 2. So here log of x plus h plus log of x can be written as log of x times x plus h, and here we have 2, right? So here we have used the important property of log, that is log of m plus log of n is equal to log of product of m and n, right? Okay, so a plus b over 2 is given by this expression, and then we can find out a minus b over 2. So a minus b over 2 is given by a log of x plus h minus log of x divided by 2. Now here we can use this property of log, that is log m minus log n is given by log m over n. So here we have log of x plus h over x, right? And in the denominator we have half. So we can write half log, and we can distribute this x to x and h. So we have 1 plus h over x. So now we have a plus b over 2 and a minus b over 2. So now the derivative is given by a limit h tends to 0 and sine log x plus h minus sine log of x is given by sine a minus sine b divided by h. So now we have limit h tends to 0, and sine a minus sine b is 2 cos a plus b over 2, and sine a minus b over 2. So now we can, here we have h also. So this is limit h tends to 0. So now we have 2 over h and cos a plus b over 2. So a plus b over 2 is given by this term. So we have cos, and then we have half of log of x times x plus h. So this is x square plus x times h, right? And this term, that is sine, and we have a minus b over 2. So a minus b over 2 is given by this term. So we have half, and then we can write log of 1 plus h over x. So here we can write half log 1 plus h over x, right? So now our aim is to find out the value of this limit, right? Now here we have three terms. First one is 2 over h, then we have cos half log x square plus xh, and then we have sine of half log 1 plus h over x. So here what we will do, we'll first write this expression like this. That is, we can now write limit h tends to 0. First we'll take this term, that is cos half, we have log, and then we have x square plus xh. So this is our first term, and then we can now write limit h tends to 0, and we can combine this term, that is 2 over h, with this sine term. So here we have sine, and then we can write half a log, and here we have 1 plus h over x, right? So now our aim is to find out the value of this limit and this limit. Now this limit is quite easy, because limit h tends to 0 cos half log x square plus xh. So here we can directly take h is equal to 0. So this term is 0, right? And we can assume this limit as L, and will separately solve this limit. So now the derivative f prime of x is given by limit. Here when we take h tends to 0, this term is 0. So we have cos half, and then we have log of x square, because this term is 0, and then multiplied with this limit, and we can call this limit as a limit L, and we'll solve it separately. So now here we have cos half, and log x square is 2 log x, and times L, and here 2 and 2 get cancelled. So we are left with cos log of x multiplied with this limit, right? And now our aim is to find out the value of this limit L. So viewers, now it is very interesting to calculate the value of this limit, where we have a log term inside the sine term, right? So to find out the value of this limit, we'll make use of the method of substitution. And moreover, to get the value of this limit, we are going to use two standard results from limits. So the first one is limit theta tends to 0, sine theta over theta is equal to 1. And the other important result is limit theta tends to 0, e raised to theta minus 1 over theta is equal to 1. So these two results are going to play a vital role in finding out the value of this limit. So let us substitute here this term, that is a half log of 1 plus h over x as theta, right? So we can now write log 1 plus h over x is equal to 2 times theta. So multiplying theta with this 2. Now we can express this equation in the form of exponential equation by raising these two terms to the exponent of e. So we have e raised to log of 1 plus h over x is equal to e raised to 2 theta. So we can now write 1 plus h over x is equal to e raised to 2 theta, and h over x is equal to e raised to 2 theta minus 1. So h is now equal to x times e raised to 2 theta minus 1. So now let us take the limit h tends to 0. So here we are given that h is tending towards 0, right? So when h tends to 0, then theta tends to half log, and here we have 1 plus h over x. So when h tends to 0, then this term, that is h over x, it also tends to 0. So we can write when h tends to 0, it implies that h over x also tends to 0. So here h over x can be written as 0, and we are left with half log of 1, and log of 1 is 0. So this is half times 0, that is equal to 0. So we conclude that when h tends to 0, then theta tends to 0. So this is quite imperative to establish this result before moving further. That is, when h tends to 0, then theta tends to 0. Because when we establish that h tends to 0 implies theta tends to 0, then only we can utilize these results, right? So we have shown that when h tends to 0, theta tends to 0. So now this limit L can be written as the limit theta tends to 0. So now h tends to 0 can be replaced by theta tends to 0, and we have 2 over h. Now h can be replaced by this expression, that is x e raised to 2 theta minus 1, and we have sine of theta, because this term half log 1 plus h over x is equal to theta. So the overall result of this discussion is that this limit, which is in terms of h, is now reduced to this limit, right? And now we can easily evaluate this limit with the help of these two results. So now this limit L can be written as, we can take 2 over x outside this limit notation, because 2 over x is independent of theta. So we have 2 over x, and then we have limit theta tends to 0, sine theta over e raised to 2 theta minus 1. So we have 2 over x, limit theta tends to 0. Now see, we can express this expression as sine theta over theta, that is dividing sine theta by theta and then multiplying it by theta to compensate. And then we have e raised to 2 theta minus 1 over 2 theta, and then here also we can write 2 theta, right? So now we can have this theta and this theta get cancelled, this 2 and this 2 get cancelled, and we have limit theta tends to 0, sine theta over theta divided by limit theta tends to 0 e raised to 2 theta minus 1 over 2 theta, right? So when theta tends to 0, then 2 theta also tends to 0, right? Here we have 2 theta. So now this limit is equal to 1 due to this result, and this limit is also equal to 1 due to this result. So we have 1 over 1, and obviously here we have 1 over x. So here we have the term 1 over x. So here we have, we can write it like this: 1 over x times 1 over 1, because this limit is 1, this limit is 1, so we have 1 over x, right? So the value of this limit is equal to 1 over x. So now the derivative of f of x is given by f prime of x, and here we have cos of log of x, and here we have L, and L is equal to 1 over x, right? So the derivative of sine log of x is given by cosine log x divided by x. So now we can write d by dx of sine log x is equal to cos of log x divided by x, right? So this is how, by using the concept of first principle, we can find out the derivative of sine log x, and similarly we can find out the derivative of the function, that is cos of log x, and this is an exercise for the viewers to find out the derivative of cosine log x with the help of first principle, and the derivative of this function is given by minus sine log x divided by x. Hello viewers, in today's session we are going to discuss another important problem from derivatives, in which we are going to find out the derivative of this function f of x is equal to sine of sine x using first principle, right? So let us start. Now see, we have already discussed a lot of problems related to finding out the derivatives of functions from first principle. So to use this first principle, we start with the definition of derivative of a function. Now see, if we have a function, say y is equal to f of x, then the derivative of y with respect to x, which is f prime of x, is given by this limit, that is limit h tends to 0, f of x plus h minus f of x divided by h, right? And here h is a very small quantity, which is infinitesimally very small, right? So we'll start with this limit to get the derivative of sine of sine x. So now we have a limit h tends to 0, f of x plus h can be obtained by replacing this x by x plus h. So we have sine of x plus h, and then we have f of x, which is sine of sine x, and here we have h. Now to simplify the numerator, we can make use of an important identity from trigonometry, right? So if we take a is equal to sine of x plus h, and b as sine of x. So let us take this sine x as b and sine x plus h as a. So now we have this identity, that is sine A minus sine B is equal to 2 times cos A plus B over 2, and sine A minus B over 2. So we'll apply this identity to simplify the numerator. So we have limit h tends to 0, and here a sine of sine x plus h. Sine x plus h is a, so we have sine a minus sine b, because sine x is b, and here we have h. So now we can write limit h tends to 0, and we have 2 times cos a plus b over 2 and sine a minus b over 2 divided by h. So here we can write h. So now we have limit h tends to 0, 2 by h, and we have cos, and for a we can write sine x plus h plus b is sine x and divided by 2, and then we have sine, and a is the sine x plus h minus sine of x, b is sine of x divided by 2, right? So now we have to evaluate this limit. Now to evaluate this limit, what we will do, we can write a limit h tends to 0, and we'll first write this expression. So we have cos of sine x plus h plus sine x divided by 2, and then we can take this expression, that is 2 over h over here. So we can now write limit h tends to 0, and we have 2 over h and sine, and here we have sine x plus h minus sine x over 2, right? So now we have the product of two limits. So let us call this limit as L1 and this limit as L2. So now let us separately find out L1 and L2. So L1 is given by this limit. Now here we have limit h tends to 0. So let us take h is equal to 0 over here. So we have cos, and then we have sine x plus 0. Then we have here sine x divided by 2. So we can now simplify it. Cos, we have sine x plus 0 is sine x. So we have sine x plus sine x, that is 2 sine x divided by 2. So now we can cancel 2 and 2. So we are left with the cos of sine x. So the value of the limit L1 is given by cosine sine x. So now let us find out the value of the limit L2. So we have limit h tends to 0, 2 over h sine x plus h minus sine x over 2. Now to simplify this term, we'll again make use of this identity, taking a as x plus h and b as x. So we have limit h tends to 0, we have 2 over h sine, and we can now write 2 times cos a plus b over 2. So we have x plus h plus x over 2, and then we have sine x plus h minus x over 2, and this 2 is given by here, right? So now this 2 and this 2 get cancelled. We have limit h tends to 0, 2 over h sine, and here we have x plus x 2x. So we have 2x plus h over 2, which can be written as x plus h over 2. So here we have cos x plus h over 2, and then we have sine x and x get cancelled, so we have sine h over 2, right? So now to simplify this limit, what we will do, we'll write limit h tends to 0, 2 over h. Then we have sine of uh, cos x plus h over 2 and sine h over 2. So we'll multiply the numerator and denominator by this term, right? So we can now write here cos x plus h over 2 sine h over 2, and to cancel out this term we'll multiply here by cos x plus h over 2 and sine h over 2. So in the next step, what we will do, we'll take this term, that is 2 over h over this term, that is here we can write h over 2. So now this limit L2 can be written as the limit h tends to 0. We have sine, then we have cos x plus h over 2 sine h over 2 divided by cos x plus h over 2 and sine h over 2 multiplied with the limit h tends to 0. We have this term, that is cos x plus h over 2 multiplied with the limit h tends to 0, and we have this term, that is sine h over 2 divided by h over 2. So now we have the product of three limits. So now let us evaluate these three limits one by one. Now see, here we have sine of this term over this term, right? That is cos x plus h over 2 sine h over 2. Now see, when h tends to 0, then we have this term also tending to 0, that is cos x plus h over 2 sine h over 2 also tends to 0. So if we take this term as say theta, then when h tends to 0, then theta tends to 0. So this limit is now equal to limit theta tends to 0 sine of theta over theta, where theta is cos x plus h over 2 sine h over 2. So when h tends to 0, then this term, that is sine h over 2, it tends to 0. So this entire term tends to 0. So it implies theta tends to 0. Then we have limit h tends to 0 cos x plus h over 2. So when h tends to 0, we have simply cos x plus 0, right? And then we have limit h tends to 0 sine h over 2 divided by h over 2. So when h tends to 0, then h over 2 also tends to 0. So again we have this form, that is limit theta tends to 0 sine theta over theta, where theta is equal to h over 2. So here the value of this limit is equal to 1, because limit theta tends to 0 sine theta over theta is equal to 1. So now this limit is equal to 1. So we have L2 is equal to 1 times cosine of x times 1. So this is equal to cosine x. So the value of the limit L1 is equal to cos of sine x, and we have just seen that the value of the limit L2 is cos x, right? And now the value of the derivative, that is dy over dx, is equal to the product of these two limits. So L1 is the cos of sine x and L2 is cosine x. So the derivative of this function, that is sine of sine x, is given by the expression, that is cos x times cos of sine x. So this is how by making use of the concept of first principle, we can easily find out the derivatives of functions.